Hello, my name is Aman Berman, and in my opinion, one of the most important and significant concepts in all of mathematics is the Taylor series. The formula for this Taylor series can be represented as f of x is equal to f of a plus f prime a times x minus a over 1 factorial plus f double prime a times x minus a whole squared over 2 factorial plus f triple prime a times x minus a whole cubed over 3 factorial all the way to infinity. And this can be represented as the summation, this summation from n to 0 to infinity of f and a times x minus a to the power of n over n factorial. So this is the general formula for Taylor series. And Taylor series can be used to deduce many functions such as e to the power of x, sine x, cos x, and log of 1 plus x, which are the most famous functions which the Taylor series can be used to represent them. So first, before we find the expansions for e to the power of x and the other functions, we should look at the Maclaurin series. The Maclaurin series is a type of Taylor series, except for the fact that a is replaced with 0. So the general formula for the Maclaurin series is f of 0 plus f prime 0 times x over 1 factorial plus f double prime 0 times x squared over 2 factorial plus f triple prime 0 times x cubed over 3 factorial all the way to infinity. And we can use this general formula to make approximations and to find the series expansions for e to the power of x, for example. Now on the side, we can write down f of x is equal to e to the power of x. Thus, f of 0 is equal to e to the power of 0, which is 1. F prime x, which is the derivative of f of x, would be the same thing, because the derivative of e to the power of x is e to the power of x. So f prime 0 is equal to e to the power of 0, which is 1. And this repeats. So if we plug that in to the general formula for the Maclaurin series, we get f of 0, which is 1, plus f prime 0 times x, which is just 1 times x, over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial to infinity. And the Maclaurin series can also be applied to sine x. And the expansion for sine x is x minus x cubed over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial to infinity. And sine x is an example of an odd function. Cos x, on the other hand, this expansion for cos x is 1 minus x squared over 2 factorial plus x4 over 4 factorial minus x6 over 6 factorial again to infinity. Now ln 1 plus x is a bit more difficult to solve compared to sine x, cos x, and e to the power of x. So I will actually demonstrate it on the side over here. So f of x is equal to ln 1 plus x. Now the derivative of ln 1 plus x will be 1 over 1 plus x. Second derivative would be minus 1 over 1 plus x squared. the third derivative would be minus 2, just 2, over 1 plus x whole cubed. And to the fourth derivative, it would be minus x over 1 plus x to the power of 4. Now, if we do f of 0, that would just be ln 1, which is 0. F prime 0 would be 1 over 1 plus 0, which is just 1. F double prime 0 would be minus 1 over 1 plus 0, which is just minus 1. F triple prime 0 would be 2 over 1 plus 0 whole cubed, which is just 2. And finally, fourth, it would be minus 6 over 1 plus 0 to the power of 4, which is just minus 6 over 1, which is minus 6. Now, if we plug that into the general formula for the Maclaurin series, we have f of 0 is 0, plus f prime 0, which is 1, times x over 1 factorial, plus f the second derivative of f of 0, which is minus 1, multiplied by x squared over 2 factorial. And then if we continue that, and that simplifies out to 0 plus, so the 0 gets negated, so that's just x plus, or x plus minus x squared over 2 plus x cubed over 3 factorial is just 6, so these two cancel, and it's just x cubed over 3 minus x4 over 4. So that plus and minus would just become minus. So that's the expansion of ln 1 plus x. Now that we've deduced all of these series expansions, e to the power of x, sin x, cos x, and ln 1 plus x, we can actually use these to derive Euler's identity. So Euler's identity states that e to the power of ix is equal to cos x plus I sin x. And we can use the expansion of e to the power of x to prove that. So we've already found out before that e to the power of x is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial to infinity. Now, if we replace x with ix, we get 1, it stays the same, plus ix over 1 factorial plus I squared x squared over 2 factorial plus I cubed x cubed over 3 factorial plus I4 x4 over 4 factorial to infinity. Now we know that I is equal to root of minus 1. So I squared is equal to minus 1, I cubed is equal to minus I, and I4 is equal to 1. So we can simplify this to 1 stays the same, 1 plus ix over 1 factorial minus x squared over 2 factorial minus ix cubed over 3 factorial plus x4 over 4 factorial. And if we do a bit of grouping, 1 minus x squared over 2 factorial plus x4 over 4 factorial minus x6 over 6 factorial to infinity. And we can take I common, x over 1 factorial minus x cubed over 3 factorial plus x5 over 5 factorial again to infinity. This is actually the expansion which we've deduced before. 1 minus x squared over 2 factorial plus x4 over 4 factorial is just cos x. So, you can write this as cos x plus I times, and this again is just sin x. So, this is sin x. And we've proved e to the power of ix is equal to cos x plus I sin x. Now that we've proved Euler's identity is e to the power of ix is equal to cos x plus I sin x, we can easily get e to the power minus ix, and just by replacing cos of minus x plus I sin minus x. And we know that cos of minus x is equal to cos of x, and sin of minus x is equal to minus sin x. So e to the power of minus x ix is equal to cos of x minus I sin x. And if we add e to the power of ix with e to the power of minus ix, we get e to the power of ix plus e to the power of minus ix is equal to cos x plus cos x, which is 2 cos x, and I sin x minus I sin x is 0. So we can represent cos x in terms of e to the power of ix and e to the power of minus ix. So cos x is e to the power of ix plus e to the power of minus ix over 2. Now that we've deduced Euler's identity, which is cos x is equal to e to the power of ix plus e to the power of minus ix over 2, we can use this to tackle Basel's problem, which is the summation of n is equal to 1 to infinity of 1 over n squared is equal to pi squared over 6, which was actually also proven by Euler. And we're going to use this tricky integral of 0 to pi by 2 ln 2 cos x dx to actually prove that the summation of 1 over n squared is equal to pi squared over 6. So we can begin by replacing cos x with e to the power of ix plus e to the power minus ix over 2. So we have 0 to pi by 2 ln 2 times e to the power of ix plus e to the power minus ix over 2 dx, which is ln e to the power of ix plus e to the power minus ix dx. And we can take e to the power of ix common inside the natural log. E to the power of ix times 1 plus e to the power minus 2ix dx. And now we can separate this integral into two integrals. Ln e to the power of ix dx plus ln 1 plus e to the power minus 2ix. Now ln e to the power of ix is just ix. So we have 0 to pi by 2 ix dx, which is just this, plus the integration of ln 1 plus e to the power minus 2ix dx. Now we can get the value of ln 1 plus e to the power minus 2ix dx by substituting e to the power minus 2ix in the expansion of the Maclaurin series of ln 1 plus x. So we just replace x with e to the power of minus 2ix. So we have e to the power of minus 2ix minus e to the power minus 2ix whole squared over 2 plus e to the power minus 2ix whole cubed over 3 minus e to the power of minus 2ix whole to the power 4 over 4. And now we can replace that in the integral. 0 to pi by 2 e to the power of minus 2ix minus e to the power minus 2ix whole square over 2 plus e to the power minus 2ix to the power of 3 over 3 plus minus e to the power minus 2ix to the power of 4 over 4 dx. So now we can easily integrate x dx, so that's just I x squared over 2 from 0 to pi by 2, and we can integrate this integral as well. So we have e to the power of minus 2ix over minus 2I minus, we can represent this as e to the power minus 4ix over 2, which is just e to the power minus 4ix over minus 8I plus e to the power minus 6ix over minus 18I minus e to the power minus 8ix over minus 32I from 0 to pi by 2. So here, the value will just be I pi squared over 8. So we can replace x with pi by 2, leaving us with e to the power of minus I pi over minus 2I minus e to the power minus 2I pi over minus 8I plus e to the power minus 3I pi over minus 18I minus e to the power minus 4I pi over minus 32I. And now, when we replace 0, we get 1 over minus 2I minus 1 over minus 8I plus 1 over minus 18I minus 1 over minus 32I. Now we can simplify this further by taking 1 over minus 2I common. So we have I pi squared over 8 minus 1 over 2I, leaving us with e to the power minus I pi minus e to the power minus 2I pi over 2 squared, so we can write that as 1 squared, plus e to the power minus 3I pi over 3 squared minus e to the power minus 4I pi over 4 squared. And we have minus 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared. And we already know that e to the power minus ni pi is minus 1 if n is odd. So we can use this rule to find the value, to replace the value of e to the power minus I pi as minus 1. So over here we can write I pi squared over 8 minus 1 over 2I. We have minus 1 over 1 squared minus 1 over 2 squared plus minus 1 over 3 squared minus 1 over 4 squared minus, we have 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared. And then we can cancel a few terms. I pi squared over 8 minus 1 over 2I times minus 1 is just minus 2. Minus 1 over 2 squared plus 1 over 2 squared gets cancelled. Minus 1 over 3 squared minus 1 over 3 squared is minus 2 over 3 squared. and this term gets cancelled. And because these two parts of the integration extend to infinity, we have minus 2 over 5 squared minus 2 over 7 squared, again extending to infinity. Now we can take minus 2 common again, so we have I pi squared over 8 minus 1 over 2i times minus 2. Now we have minus 1 over 1 squared minus, 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared, etc. So now we have I pi squared over 8 plus 1 over I times 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared, etc. So now we can rationalize I, multiplying it by I over I, giving us with minus I. So we have I pi squared over 8 minus I times 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared. Now so first we can take I common. So we have pi squared over 8, again minus 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared. Since this integral results in a real value, the coefficient of the I terms must equal 0. So we have pi squared over 8 must equal 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared. And since we are looking for the summation of n is equal to 1 to infinity of 1 over n squared, we can represent that as s. So s is equal to pi squared over 8 plus 1 over 2 squared plus 1 over 4 squared plus 1 over 6 squared plus 1 over 8 squared. Again, extending to. And now we can take 1 over 2 squared common. So we have s is equal to pi squared over 8 plus 1 over 2 squared common, and that leaves us with 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. Now this is just s. So if we come down here, we have s is equal to pi squared over 8 plus 1 over 4s. Thus, if we take 1 over s to the other side, we have 3 over 4s is actually equal to pi squared over 8. And if we divide both sides by 3 over 4, we have s is equal to pi squared over 6, which is exactly what we were looking for. So now we have used the integration of ln to cos x dx from 0 to pi over 2 to actually prove the Basel problem, which is the summation of n is equal to 1 to infinity 1 over n squared is equal to pi squared over 6.